Welcome everyone to the next webinar installment from Risk Management Professionals. My name is Jose Chavez and I'm a project engineer with Risk Management Professionals. For this webinar, we'll be analyzing important information regarding pumps for use in a process hazard analysis. This may be helpful if you're preparing for an upcoming PHA or are looking for clarity as to the calculations involved in pump failures. The agenda for today's presentation is to first summarize the process hazard analysis and what's required. We'll then discuss the first pump failure type, cavitation, and what the NPSH is. Then we'll discuss the other failure type, pump deadhead. Both of these failures and their calculated limits will prove useful for the hazard analysis. The process hazard analysis, or PHAs, is a requirement for facilities subject to 40 CFR Part 68, EPA Risk Management Plan, as well as 29 CFR Section 1910.119 OSHA's Process Safety Management Program. In a PHA, process safety hazards must be identified. This includes reviewing previous incidents that may have occurred on-site or in the industry that may be relevant. It may include review of the engineering or administrative controls and the consequences of these failures as far as the health and safety of personnel and the public, environmental impacts, and equipment damage. Also included are facility siting, human factors, and natural hazards. So what is the information we need for a PHA? For one, we want to look at how the system is intended to operate, with operating temperatures, pressures, and levels. We also want to note the design temperatures and pressures to see what we shouldn't be exceeding. We may also want to find the maximum and minimum conditions that can be generated, see if the system can physically go beyond those design conditions. We may think that since we don't operate high enough temperatures or pressures, we wouldn't have to worry. However, the PHA isn't evaluating everything working as intended. It's evaluating failures of those controls and those consequences. Operating parameters can be found a few ways, the easiest being through the HMI, whether that's a DCS system or SCADA, seeing the values on screen, or going into the field and seeing what the equipment is set to and what gauges are reading. For design parameters, this can be found in the latest field-verified drawings or on equipment nameplates. The third set of information we may want is the maximums able to be generated. These may need to be calculated during the PHA as the scenarios are discovered. For example, liquid filling a vessel puts more static pressure on other equipment. Using the static pressure equation, height times density times gravity gives us an idea of the pressures we'll see. We may need pressure and temperature calculations from reaction chemistry for runaway reaction scenarios. Compressors can be damaged if blocked in to certain pressures. Pumps have NPSH requirements that, if not met, lead to cavitation, and pumps can also be blocked in and be damaged due to deadhead. Focusing on pump failures, the first is pump cavitation. The key is net positive suction head, NPSH. More specifically, what head is required, NPSH-R. In order for the pump to operate, it must have sufficient pressure coming from the suction side. If it experiences a drop in pressure, either from a feed drum losing level or a suction valve being closed, NPSH will approach and eventually fall below the NPSH-R. If it goes below, the liquid can begin to boil. When the bubbles collapse in the pump, they cause damage to the metal. This is called cavitation. And if it persists long enough and is severe enough, it can lead to a release and a potentially hazardous event. NPSH-R can be found in manufacturer data in the pump curves. NPSH-R will increase as flow increases. The operating pressure at the suction, which correlates to the NPSH-A, can be estimated using friction loss, vapor pressure of the stream, and most importantly, the pressure source. The pressure source may be a hydrostatic pressure from a vessel, which can be conveniently calculated. It can be what the upstream pump or regulator is manually set to. To put this into numbers, NPSHA is equal to the atmospheric pressure plus the hydrostatic pressure based on liquid level minus the total friction loss in the pipes, valves, fittings, strainers, and other equipment minus the vapor pressure. In most systems, the first two will give you a close enough estimate to see if you'll have any problems meeting the NPSHR. The second failure to cover for PHA is pump deadhead. Upon blocked discharge, certain pumps may release material depending on the pump type, pump curve, and piping specifications. Blocked discharge can occur due to valve closures, downstream pluggage, or inability to move liquid due to another competing source of pressure. For a positive displacement pump, liquid may continue to be pumped, eventually rupturing discharge piping, and for centrifugal pumps, the pump internals may become damaged, leading to a possible seal leak. The design pressure for discharge piping can be determined from pipe spec charts and flange ratings. Design pressure of downstream equipment can be determined from P&IDs and other engineering drawings. And the maximum pressure to be produced can be determined from the manufacturer pump curve. We'll want to see at the no flow point what will be our highest pressure. Here is a fictional pump curve as an example. To find our deadhead, we find our impeller line, in this case a 10-inch impeller. We follow that to where the flow approaches zero, and we'll see the maximum head able to be produced. This would only be done by accident, as it is highly inefficient and possibly hazardous. We convert head to pressure based on the material being pumped, add our suction pressure since the graph is only a differential, and now we have our deadhead pump pressure. With deadhead pressure calculated, we can see what, if any, damage may occur to the pump, piping, or downstream equipment. I've listed our references here on pumps, and for more information on PHAs, PSM, or RMP, visit our website at rmpcorp.com or reach us at the numbers below. If you'd like more webinars on PSM RMP related topics, you can also subscribe to our account. This is Jose Chavez. Thank you, and stay safe.